Hey, hello guys, welcome, vanakkam, vandanam, namaskaram. Today we are going to see chemical kinematics part 1. I will try my level best to complete this total lesson in this one video itself, like one short video. If my leg supports, I'll be supporting you all with this one video. If I can't, then I have to break this video into parts. Okay, so chemical kinematics. Very easy lesson. If you are able to understand physical chemistry, then this lesson is going to be very easy. Just like electrochemistry, this is a part of physical chemistry where you'll be reading about collisions, you'll be reading about a lot of things. In thermodynamics, this is having a lot of contact with thermodynamics. Yeah, we will see everything. First of all, we will start with thermodynamics. Okay. So, what is thermodynamics? We have studied this lesson in our class 11 itself, right? So we need not to say that much. We'll just discuss some points about thermodynamics. With this thermodynamics, we can easily say whether a reaction is spontaneous or non-spontaneous, or at equilibrium. Okay, or at equilibrium, right? Okay. See, in the spontaneous reaction, what are we having? Okay. In the spontaneous reaction, the delta G value will be always negative. Okay. In the non-spontaneous reaction, delta G value will be always positive. Okay. In the equilibrium reaction, delta G value will be always 0. Okay. So delta G value will be always 0. This is what we have to discuss. And also, what is this equilibrium? Just one point. We will just check it out. Equilibrium is a dynamic state. Okay, it is a dynamic state where rate of forward reaction will be equal to rate of backward reaction. Okay, is equal to rate of backward reaction. Okay, so this is what the equilibrium state is, and moreover, this is actually used to write the feasibility or the flexibility, we can say, of a reaction. Okay, so yeah, these are the basic points that you have to know about thermodynamics. Then coming to chemical kinematics, this chemical kinematics is actually explaining a few parts. That is, first is okay. So the first one is, it explains how fast a reaction is. Okay, the rate of reaction can be calculated by using chemical kinetics. Okay, and also we can easily say that what are the factors that are affecting a reaction. Okay, factors that are affecting a reaction. Then also we can say that it is actually we can say how fast is a reaction, and also the favorable conditions for a reaction in order to get the good yield. Okay, so the favorable conditions in order to get yield. In order to get good yield. Or good amount of okay, so in order to get good amounts of products. Okay, so these are those basic things that you have to know. I think I've taken a lot of space for this itself. Okay, so before going into this concept, or this lesson, I would suggest you all to go into solution chapters. Okay, solution, even I've very clearly explained what is the concentration, what are the concentrations, like what is molarity, all those concepts we have very well explained. But it's okay, I don't want you all to go and check that video again, as you all are just like me, right? So we will just check it out here itself. Okay, so in the concentrations, okay, concentrations. Which color can we use? We should use light pink. Okay, so in the concentration, first is molarity. Just molarity, no molality, only molarity. Okay, so just molarity. So what is this? Molarity can be said as number of moles is equal to number of moles of solute, okay, whole divided by volume of solution in liters. Okay, in liters, this is what molarity is. See, molarity itself is actually of two different types. Okay, so it is just normal molarity, which is this one. Okay, normal molarity. Okay, and then millimolarity. Okay, millimolarity. So millimolarity in sense like how it will be. See, it is actually very simple. The same formula only. Mole, number of moles whole divided by volume of solution in terms of liter. Okay, it is actually having the same formula only, but the thing is, your number of moles will be millimoles. It is millimoles. Okay, so what is millimoles? Millimoles is actually where 1 mole. Okay, 1 mole is equal to 1000 millimoles. Okay, so it is equal to 1000 millimoles. Okay, next is there is another point. That is where we can say that 1 liter is equal to 1 dime cube, which is equal to 1000 ml, which is equal to 1000 centimeters. Sorry, 1000 centimeter cube. Okay, so which is further equal to 1000 cc, cubic meter. Okay, sorry, cubic centimeter. Sorry, is equal to 1000 cubic centimeter. This is what the note point is. You can just note it out. Okay, so millimoles is equal to, okay, so we have seen. Next is concentration, also the amount of solute present in 1 unit volume of solution. Okay, the amount of solute that is present in 1 unit volume of solution is what the definition of molarity is. Okay, so coming to here itself again. So pH, now we are going to see about pH. Not that much points are there about pH. Okay, only a few points are there. We will just discuss those few. See, pH is equal to minus of log of hydrogen ions. Okay, minus of log of H plus. Okay, sorry. H plus ions. Okay, POH is equal to minus of log of OH minus ions. Okay, so how will you concentrate? Actually, how will you calculate the concentration of H plus and OH minus? For that, what you have to use is to calculate the concentration of OH and then OH minus. What you have to use is, okay, normality you have to use. Okay, you have to use normality. Okay, next is pH is equal to minus log of H plus, and then POH is equal to minus log of OH minus. Okay, ma? Taka. So here, which can be also written as? Okay, so you have to note this point, that is H plus is there, right? That is equal to, just take it over there. So in that case, it will be 10 to the power of 10 to the power of what? Minus pH. Okay, OH minus is equal to 10 to the power of minus POH. Okay, like this also you can calculate. We all know, right? The opposite of log is what going to be the exponential function. Okay, so it is log function and here it is exponential function. About functions also, I don't think I can upload a video in mathematics as I'm not that much strong in maths. Personally, I don't like to teach maths either because of some incidents. So yeah, in mathematics, maybe one video I've uploaded based on relations and functions, but hereafter it's very tough for me to upload videos based on mathematics as I don't like to teach mathematics that much because of some incidents that happened in the school. Okay, I'm saying the same sentence again and again because it has affected me. Okay, so coming back to the reaction. See, this is what a reaction is, where the reactants will be converted into products. Okay, will be converted into product. This is what normally happens, right? Okay, so which means in the very beginning, we can say that this will be reactants will be more in concentration, or only reactants will be okay in the beginning. What the way that how we represent in the beginning is that, or not you can represent. Okay, it means that the reaction has not even started, or it means that the reaction has started, but the time hasn't passed away. Maybe at most, maybe 0.1 seconds like that it could have passed. Other than that, it wouldn't have passed. Okay, so it means in the very beginning, the reactance amount is this one. Okay, so this one will be, let us keep that it is 1. Okay, let us keep that it is 1. And in the same time, the products amount will be 0. Okay, the products amount will be completely 0. So as the time passes, the reactant, okay, so this one reduces with time. Okay, this one increases with time. Okay, I'm so sorry if you're just getting a tuck 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 noises. I can hold this pen and I can write like this also, as it also gives me good handwriting. But the thing is, I'm more comfortable to write in this way than to hold it like this and to write. Okay. So now we are going to see rate of reaction. Okay, now we are going to see rate of reaction. Where rate of reaction, okay, this is not that much comfortable. Okay, see, rate of reaction is equal to the change of products, or the change in concentration in products or reactants whole divided by time. Okay, whole divided by time. That's it. Okay, I'll write here change on products. Okay, or also can be said as reactants. Mostly we'll be taking reactants only than products. Whole divided by time. Okay, total time with unit time. Okay. Whole divided by unit time. So this is what the rate of reaction is. See, it means concentration per unit time, right? So it means, see, what is concentration? Concentration can be said as molarity. That is what we have discussed over here. Okay, so what is molarity? Molarity is mole per liter, right? So here concentration, we are calculating, we are trying to calculate SI unit. Okay, we are trying to calculate SI unit. See, SI unit is what over here? SI unit is actually, first is molarity. So molarity is going to be mole per liter. Okay, whole divided by time. So time will be seconds. It will be in seconds, right? So if I have to write this, if I have to write in another way, so that means molarity. So it can be done in a like this. It can be done so by 1. So molarity by liter into 1 by second. Okay, so which means that molarity liter inverse second inverse. So mole liter inverse second inverse. Okay, so this is how you are going to calculate the SI unit, and as I've calculated over there. Okay, so after this we are also having it's very hot over here. I can't even switch on the AC or I can't switch on the fan since I'm taking video and the voice of the video quality will be broken if I just switch on any of them. So I'm just sacrificing. Okay. So anyways, it's not a problem. Coming to the terms of okay. So formula. So rate. See, this formula is different for reactants and also for products. For product it is one formula and for reactants it is another formula. Okay. So first is for reactants. Okay. So reactants in sense, how it will be, we already know that with time the concentration of the reactants completely decrease, and I forgot to say one thing. Sometimes whenever in case I'm just saying some basic things, my voice may change. So just don't mind it. Okay, so here it is a basic thing. Anything that is represented in chemistry with its closed brackets, that is used to represent the concentrations. Okay? Okay, perfect. So now coming to reactants. So I've said that with in terms of reactants, the concentration will be decreasing, right? So for that one, what you have to do is you have to put negative sign. Okay, first you have to put a negative sign to represent the decrease in concentration. Okay, then what is the formula for rate of reaction? The change in the concentration of products, right? Okay, so what is change? Change can be represented either by D or by delta. Like this, it can be represented. This is also a very basic thing only. So D will be used for very minute changes. D will be used for very minute changes, whereas delta can be used for big changes, as it's sorry, yeah, correct. So delta, I can write here delta in the concentration of reactants whole divided by change in time. Okay, whole divided by change in time. This is what we say. The change in concentration of reactants whole divided by change in time. Okay. Now after this, also coming to reactants, coming to products. So what is this? Here, as with time, the concentration of products increases. So in order to represent it, I can give here a plus, and we can write the same formula, which is dP. You have to write concentration of product whole divided by dt. Okay, so this is what the formula for rate of reactants and rate of products. You can get it out. Okay, so now we will just do a small numerical based on an equation that let me give. Okay, I'm going to erase it as it is a numerical. 2a plus 3c gives rise to, no, this is rate of equation. Okay, at last we will be doing sums based on this. At last, in the very beginning, we will do sums, or very simple. See, in the very beginning, they would have given you a concentration. That is, see, A was initially at around how much? 15 moles we can take? Okay, 15 moles. Okay, then after some t time, it has become into 7.5 moles. It has become into 7.5 moles. That means this minus this. Okay, so this minus this, which is actually, see, always this is what rate 2, and then this is rate 1, this is time t. Within this time it has decreased. So rate of reaction is what? Rate of reaction is equal to R2 minus R1 whole divided by t time. So t time, let us assume that t time is actually 7.5 seconds itself. Okay, 7.5 seconds itself. And also here minus should be coming, right? Okay, so here that means 7.5 moles minus 15 moles. Okay, here minus whole divided by 7.5 seconds. Okay, here it will be always given in seconds. If it is not given in seconds, try to convert it into minutes, and then sorry, if it is not given in seconds, then it would have been given in the form of minutes. Then try to convert it into seconds and then proceed with the sums. Or if it is an MCQ question, and in the question if they have given in that essay unit, if they have given it as minutes, then let it be in the minutes itself. Okay. So now what it can be written? It can be written as minus 7.5, like this minus, and then here also it is going to be minus whole divided by 7.5. So this and this will be cancelled, so it will be 1. So from the sum, what can we say? We can say that rate will be always positive. No matter what, rate will be always positive. That is why we have given there negative sign and positive sign. In order to get rate always positive, we have put there minus and plus sign. Okay, so this is a note point, that is rate will be always positive. Okay, so next concept is that now we are going to draw a graph. Okay, so this graph will be different for reactants and products. First is reactants. Okay, so this is for reactants. We all know that with respect to time, the concentration of reactants will always decrease. So I will be drawing a graph like this. So initially, the very initial, the concentration of reactants will be here. Okay, at this point, let us keep. So with time, with respect to time, they will be decreasing, and they would have reached to a particular limit. Like this, it will be going on, and we will stop it here itself. Okay, so we will just stop it over here itself. So this is how the reactants are. We will be still some terms that they to discuss. We'll discuss, but before that, we'll just complete this. Okay, so whereas for products, it will be starting with here. Okay, as in the beginning there won't be any concentration of products. As with time, just increases. It will stop by here itself. Okay, ma. So initial concentration. This is what. So which means it has to be represented with or not. Okay, so this is what the final concentration is. So it can be represented as R. Here also it should be represented as P naught with P. Okay, so P naught and then with P. Okay, see, initially in the very beginning, the time would have been T1 and 0 seconds. Here T2 it would have been at some x seconds it will be. Okay, so here also T1, this point is what T1 will be 0 seconds, and with some time it will be T2 where with some x seconds. Okay, ma. Okay, so this is how the concept is. Very simple, right? Just this one graph. Okay, then after that is, I've given you the SI unit of rate. Next is chemical reactions classification. See, chemical reactions are classified into slow, fast, moderate, and elementary reaction, complex reactions. Where slow, fast, moderate is based on time classification, and elementary reaction, complex reactions are based on the number of steps of a reaction. Then order reactions, okay, based on the order of a reaction. You'll discuss what is order. Okay, order, all these. Okay, based on these, a chemical reaction is classified. Okay, so classifications of chemical reactions. So with this one, we will end this video. Okay, with based on this classification of chemical reactions, we will end this video. As my leg cannot do that much. So chemical Okay, so chemical reaction classification. What is this concept? Okay, so what is this chemical reaction classification? As I said that first it is classified into, first we will classify this with just a little bit of font size would help. Okay, so first classification is based on timeline. Okay, so totally there are three different steps. First one is going to be slow reactions, very slow reactions. Okay, next one is going to be moderate reaction. Next is fast reactions. Okay, so first is slow reaction. What is this slow reaction? That takes a large period of time in order to complete a full reaction. Okay, see, a reaction that will be taking a large period of time. That is what we'll be saying as slow reaction. The rate determining step is in the moderate reaction, not here. That you have to note. Rate determining step will be always in the moderate reaction. Just because I'll be saying that very clearly. But just to note this point, that rate determining step will be always in the moderate reaction, neither in the slow reaction nor in the fast reaction. Okay. So it can take some days till 2 years itself. Okay. But whereas fast reactions will take just within seconds, within fraction of seconds, will be completed. Seconds and at most minutes. Okay, here we'll be taking some hours. Okay, some hours we can say, or yeah, that's it. Some hours. Okay, so this is what the timeline is. Coming to slow reactions, what are the examples that can be given? Corrosion of metals. Such as, like, I can also give example of rusting. Okay, then after that we are having plastic decomposition. Okay, actually for plastic decomposition we have to classify a separate reaction itself. You can also add it in slow reactions, but since plastic decomposition will be taking over centuries and centuries, I think somewhere I've read it about it will be taking around 1 millennium years. I don't know whether it is true or not, but plastic decomposition is very, very, very slow reaction. That is why plastic has entered into our biosphere. A biosphere in sense, not biosphere, sorry, biological system, I can say. Okay, the food web, we can say. Already in our bloodstreams, we can easily find microplastics. Fishes are eating plastics. It's a very dreadful thing, but even though we are using it without any concern for nature, for environment, it's something that just gives heartaches to environmentalists. Even it gives angry to me. Okay, so coming back to the topic, that is next is also silicate decomposition. Okay, so silicate decomposition in sense what? Silicate, like glass, can be given as an example, and also silica cannot be decomposed. For an example, if in case we humans, we living creatures, had been made up of silica, then we could not face destruction. We cannot be destroyed. Okay, that is why diatoms in class 11th. Okay, and biological classification we have studied about diatoms, right? Diatoms are having that silica wall, which is soap box like structure, right? We have studied now. So that one is that wall. Okay, the wall of the diatoms is actually like soap box like structure. So it'll be like this. So this wall is actually made up of silica. So in sense, even though the internal organs are not made up of silica, just the external layer is made up of silica, these internal organs would have died with time, okay, with some factors would have died, but the silica will be remaining as such. So that is why this earth is also known as diatomaceous earth. Okay, so silicate decomposition. And also, as I said, that if in case we were made up of silica, then we wouldn't have evolved. Maybe we will be indestructible, but we wouldn't have evolved. Next is modern reactions, which okay, we will complete with fast, then with modern reaction. So what is fast reaction? It just takes within just some fraction of seconds. Best example is actually crackers, weapons such as bombs, such as guns, okay, such as grenades. All these are very good examples of fast reactions. Explosives, precipitate reactions, yeah. Neutralization, precipitate reactive, and also ionic. Okay, so ionic, precipitation, oh, and then neutralization. Okay, neutralization. These are the best examples. Whereas for moderate reactions, we can actually give covalent reactions as the best examples. Why so? Why ionic reaction is in the fast reaction list and why covalent reactions are in the moderate reaction list? It is because, see, here new bond formation, this also varies. Okay, this is actually a very good person, that is why I'm writing here. Okay, here new bond formation takes place. Okay, but whereas over in the ionic, only exchange of atoms takes place. Okay, exchange of elements, I can say. Okay, exchange takes place. Okay, so it seems God is not supporting us. I will talk to you within 5 minutes. Okay, so the current has come, and absolutely it came a little bit earlier even, but I was the one who is immersed in YouTube. Okay, so coming back to the moderate reaction, so it will be happening in hours, or yes, right, it will be happening in hours, and actually it is actually covalent reaction. Okay, so moderate reactions are, it can be complex reactions also. Moderate reactions can be also complex reactions. Okay, so as I said that it can be also complex reaction. So what is a complex reaction? See, if in case a reaction is there which is having more than one step, that is known as complex reaction. So that means, wait a second, we will talk about here with complex reactions. Elementary reaction then the complex reaction. Okay, see, first what is an elementary reaction? It is a single step reaction. It is a multiple step reaction. Okay, so here reactants are changed into directly products. Okay, reactants are directly changed into products, but whereas here it is not like that. Best example is that O3 is there, right? So this O3 can be undergoing this decomposition reaction, and then it can form O2 and then nascent oxygen. Okay, so when this nascent oxygen is combined with this O3, then it gives us then it gives us 2O2. Okay, then it gives us 2O2. Okay, so here rate is directly proportional to concentration of reactants. So in order to remove this concentration, what we will be doing, we will be actually putting a constant, right? So here also I can give a constant called K. Is what rate is. Okay, is what rate is, and also in some cases it is also said as rate equation. Okay, rate equation will be also like this only. We will be studying about rate equation also. Okay, so this is what one complex reaction is, this is what elementary reaction is. So for elementary reaction, what is the best example? Hydrolysis is a very good example. Okay, hydrolysis is a very good example. All single step are a very good example. Next is yeah, so about this one, since I'm personally an environmentalist and also it seems my chemistry set also likes nature, so he has given some points. He normally gives his advice based on how to protect nature, all these things is. So yeah, we will be also checking about one important note fact. Okay, well this is not in the portion, but it's okay since he has given, and since I'm an environmentalist, well I say I'm an environmentalist, but I have planted less plants only. We will do that together one day. Okay, so coming to examples, coming to that note point. See, O3 is what? O3 is ozone layer, right? So this O3, this ozone layer can be depleted by CFC, chloro, Cl, so it can be depleted by chlorofluorocarbon or by nitrogen monoxide, okay, or by nitrogen monoxide. So it is actually this chlorofluorocarbon is coming from AC, it is coming from fridge, it is coming from these, okay, devices, and also there are some fridges, there are some ACs which do not produce chlorofluorocarbon. That ACs and those fridges are preferred. And also nitrogen monoxide is also produced by devices, okay, and mostly the pollution happens. The pollution is the main cause of depletion of these ozone layer molecules. Okay, I have heard that somewhere one CFC molecule can destroy about 1 million O3 molecules. I've read it somewhere. Then just imagine how much big thing we are causing to this universe. Okay, so this is what complex and elementary reactions are. So moderate reaction can be mostly it will be complex reaction only. Okay, so complex reaction in sense it will be two-step reaction. Okay, it will be two-step reaction. That means first step will be happening and then next step will be happening. Okay, so amongst this, which is the slowest reaction? Okay, so which is the slowest reaction? That is what known as rate determining step. Okay, so which means see here amongst this, these are those two different equations, right? So here this is what is slowest reactions. Slowest reaction. Okay, so this is what very slow, and then this is fast. No, not slowest reaction, just slow reaction. Okay, slow step. This is fast step. Okay, so this is fast step, this is slow step. So this is what going to be rate determining reaction. Okay, so this is what the rate determining step is. So that means based on this slow reaction only, we can easily determine the total reaction itself. Okay, the rate of the reaction itself. So here, which means amongst this, so since this is a complex reaction, complex reactions, amongst this, which is the slowest one? Okay, which is the slowest reaction? That is going to be rate determining step. Okay, or rate determining and predetermining step. Okay. Next is coming to the examples of moderate reaction. This is the best example. What are the best examples? So for moderate reaction, I can easily say hydrolysis. Okay, no, so yeah, ester hydrolysis. it still hydrolyzes in sense. This is what is happening with fruits. My sir said. See, every point that I'm saying is said by my school chemistry teacher. So you have to understand it. Since I'm a student, I cannot just go and I cannot just read a book and I cannot understand. I will listen. I will just come here and I will take it. Okay. So hydrolyzes in sense. See, the fruit smell that we get in any fruit shop you are going, and if you're just going inside the fruit shop itself, you'll be able to get the fruit smell, right? That is because ester is being hydrolyzed, and the one and only, not one and only, a very very important thing is that this is reversible reaction. Okay, this is reversible. So this is reversible. Okay, there are also other examples. So other examples in sense like what? Digestion of food is there. Okay, so digestion of food, that is also moderate reaction when we. Then after that, milk converted into curd. Okay, so these two are. What are these? So these two are irreversible reactions. I think I'm very close to board, just like I'm kissing the board. Okay, so never mind, don't think like that. Coming to the next one, so we have completed this one. Next is we have also completed elementary reactions, complex reactions. We have still rate equation that we'll be discussing. Before that, we'll be discussing about the factors that are affecting a reaction. There are a lot of factors to discuss. Okay. Factors affecting the rate of the equation. Okay. Rate of the reaction we can take. Okay. So rate of the equation. Okay. So the first one is that temperature. Okay. So how does it? No, this handwriting is not at all good. So what is the relation between rate, the temperature and then the rate of the reaction? It is actually directly proportional. So temperature is directly proportional to rate of the reaction. Okay. Next, after this is concentration. Which is also directly proportional to the rate of the reaction. Next, after this is, so concentration, there is an example. Okay, so there is an example that is diluted HCl is there, right? So HCl, with that if you are adding zinc, then it will be giving you ZnCl2 plus H2. Okay, so since Cl2, H2, I will put here 2. Okay, so this is what the equation is, and this is diluted. Okay, and if I take a concentrated 2HCl, and if I just add it with zinc, then it will also give me ZnCl2 plus H2. Okay, so plus H2. But the thing is, here this reaction and this reaction, there is a difference. That is, this reaction is going to take part in a very slow. Okay, this is a slow reaction. Yeah, but this is a fast reaction. This is a fast reaction. That's the difference. Okay. So after this, rate of the reaction is directly surface area. So surface area intensity, very simple. Let us take evaporation itself. There is this tub and then there is this one tub. This is a tub and then this is the tub. Okay, so I've filled here water. Here also I've filled completely water. Okay, evaporation starts to take place and I've kept it in sunlight. Okay, so this is what the sun is. Okay, so automatically, okay, my sun is very beautiful. Okay, now it is very good. Okay, so here the rate of evaporation will be very less in this one, but the rate of evaporation in this one will be very high because the surface area is very high. Okay. We can also say that here it is not collision, here it is just increase in temperature. So just because of increase in temperature, the bonds are being broken, and then liquid state atoms are being converted into gaseous state atoms. But here collision, the space for collision will be high if the surface area is high. So we can say that surface area is directly proportional to the rate of the reaction. Okay, so just rate. So after that, reactivity order of states of matter. Okay, so in this case, see, the reactivity of gas will be very high comparatively with liquid, and the reactivity of liquid will be very high comparatively with solids. Okay, so that is why in hospitals and in medicines, in hospitals and then in pharmacy shops, injections will be given in the liquid state so that the reactivity will be very high. And also, when you are having cold, they will be giving you that steam, right? That will be in gaseous state. Okay, the medicine will be in gaseous state, so that will be acting very fast, and it can react with the cold and it can protect. So we can say that. So for gas, it will be very high, then for liquid, and then at last, it will be for gas. G, solid. Okay, then it will be for solid. Then after this reactivity order, we are also having, the rate is directly proportional to pressure only in gases. Okay, only in gases, rate is directly proportional to pressure. Okay, see, pressure I have to write now. Okay, so the rate is directly proportional to pressure. Then after pressure, what we are having here? Yeah, well, I said right in the covalent. Did I explain it completely, or did I just leave it out? I don't know, since it had taken place before the power off. I don't know, but it's okay. We will write here. I'm going to erase it, but it's okay. You can just listen out. In an ionic reaction, for an example, AgNO3 plus NaCl. This is a reaction that I can take. So here, what happens is the bond between NO3 and Ag will be like this, and NaCl and then Na and then Cl will be like this, right? So here, what happens is this Ag is substituting this. Sorry, this Na is substituting this Ag, and this Ag is substituting Na. So just a substitution takes place. Other than that, nothing takes place. So that this ionic reaction will be very fast. Ionic reactions will be very fast. So because just the substitution of ions is taking place. Okay, whereas in the covalent bond, it's not like that. I can take R single bond carbon, single bond R double bond. Okay, plus so that's it. So when it is being hydrolyzed, when it is being hydrated, H2O, when you are giving H2O over to it, what it becomes is the bond here, it is broken. The bond which is over here is broken. So if you're just breaking the bond, it will be here bond breaking and bond formation is taking place. So that is why this covalent reaction is actually a little bit slower than the ionic reaction. Okay, next is based on rate chemical reaction. What is rate chemical reaction? There is instantaneous reaction and then average reaction. So what is this instantaneous and this average reaction? See, instantaneous reaction is something which takes place in that particular moment, in that particular timeline, okay, in that particular second we can say. So to this what we have to use? The formula is going to be rate is equal to dr whole divided by dt. Whereas for average reaction, the rate is going to be delta r whole divided by delta t. Very simple, right? Very easy, right? So this one is actually a very small interval of time. Okay, very small. But whereas this a medium amount of time. Okay, a medium amount of time can be set, and this will be very accurate. Okay, but this will be precise. Okay, so that's the difference between this and that. Today morning, I had woken up about 4 o'clock. Well, my parents woke me up. They just shook me up. That is why I woke. Since I have to go to temple today and the next week day, so I'm kind of tired. But my parents slept very well. Okay, so coming to the rate equation. This is the last topic that we are going to discuss. Okay, rate equation. Don't think that I woke up at 4 for studying. That will not happen. 4 o'clock in the morning is not good for health for me. 7 hours of sleep. Okay, so today I didn't sleep. Okay, coming back to the concept. What is rate equation? Rate equation, for an example, they have given you some sort of equation, some sort of reaction we can take. A2A plus 3B gives rise to 2C plus 3D. Okay, so this is what? No, 3, always 2 and 3 is what they. So we can take that just C plus 4D is what the equations. Okay, so what you have to do is, first you have to neglect all the reactants. Okay, first you have to neglect all the reactants. That is something that you have to do in the very beginning. Then after that, what you have to do is, see, you have got these two now. So first you have to write rate. Okay, rate is equal to K. It is a constant. Okay, it is what a rate constant. It is known as rate constant. That is what we have seen over here. Rate. Somewhere I wrote. I said, see, in the elementary reaction I have written this K. Now that is what this K. So K into A, concentration of A into concentration of B you have to write. Concentration of A into concentration of B you have to write. And to the power of A you have to put 2 since the concentration of A is 2. The coefficient, stoichiometric coefficient is 2 and here the stoichiometric coefficient is 3. So you have to put here 2 and 3. So this is what the rate equation. Okay, this is what the rate equation is. Okay, so also there is this rate. Okay, just the rate. Here this is actually rate equation. Here it is the rate equation. Now we are going to compare the rate of formation, rate of disappearance of each and every element in a reaction. That with that you will be ending. Okay, so this is what the rate equation is. Next is rate of formation, okay, whole divided by rate of disappearance. So the same reaction I'm going to consider, which is 2A plus 3B gives rise to C plus 4D. Okay, so this is what the reaction is. Okay, this is what the reactional equation is. So with this, the rate of formation, this is what? For these two we are going to represent the rate of formation, and then for these two we are going to represent the rate of disappearance. Okay, ma'am. So first you will start with rate of disappearance itself. So for this, in order to represent this, you have to use this formula only. Okay, you have to use these two formulas only. So with these two formulas, we are going to calculate this one. Okay, so first is negative. Okay, negative you have to write for A. Okay, negative of A whole divided by dt. Okay, into 1 by 2 you have to write. since here the concentration of A is 2, so you have to just reciprocal this 2 into 1 by 2. That means the reciprocal of 2 is 1 by 2, right? So you have to reciprocal it, then it will be giving you this value. Okay, which is equal to what? Minus 1 by 3 into concentration of B whole divided by this time. Okay, so which is further equal to, so these two are rate of disappearance. So since reactants will be disappearing, we will be saying that these two are rate of disappearance. Now coming to rate of formation, which is plus 1 by 1. Here 1 is there, so reciprocal of 1 is 1 by 1 into concentration of C whole divided by dt is equal to at last plus 1 by 4 into concentration of D whole divided by concentration whole divided by this time. Okay, so this is what you are going to get. Okay, so if I just neglect all these into marks, okay, and just write it, then it's going to give you the answer, which is going to be like this. Okay, minus 1 by 2 concentration of A by time is equal to minus of concentration, okay, 1 by 3 into concentration of B by dt, which is further equal to plus concentration of C by dt is equal to concentration of D whole divided by 4 d. So these are those. That's it. Very simple. Very easy. Okay. So at last, with the basic definition of order, I'm going to complete. Okay, with the basic definition. Order we are not touching, but just the basic definition is. See, here you are having this number and in this number, right? The sum of square of the products of the reactants is what known as order. That means the sum of the squares. That means, see, the order of this reaction is going to be 5. Because 2 plus 3 is going to be 5. 2 plus 3 is going to be 5, but there is no sum based on order 5 at all. Our concept ends at order 3 itself. Okay, order 3 itself is at max. Order 0 and order 1 is very important. Derivation of those formulas. What is order? Okay, with order we will be completing with the next video. Okay, this one, that's it, completed. Around 1 hour I've taken. So thank you, bye bye. I hope it was helpful, and if there is any doubt, please feel free to ask. Okay, bye bye. So I'm going to